this session. She's so happy to be with us, and so our first speaker for after the break is Austin Sherbola, and he will be from North Carolina, believe it or not, so like most of our speakers today for some reason, and so he will tell us some new stuff about Lavoisier.
Thank you. Thank you all for being here. I love this philosophy. You can find where I'm going to read at Independent with / my last name. There's a copy of this book. I'll get into the book as well. This is really going to be just like a walk in the park for me. This is concluding about a year of research, explanation, and trial. Been to a couple other conferences. This is going to just touch on something I found along the way. I hope to share with you. I might go full time. I might not make everything, but we're going to hit the main points. We're going to go over the first 3 paragraphs of this book, which I'll talk to you in a second. Elements of Chemistry, one of the first, probably the first chemistry textbook ever. We'll get pictures in a second. But this is where I think Lavoisier's real philosophy comes to shine, of his connection of science and language. So we're really going to tackle into this. Then we'll go into how he defines an element, and from the parentheses, these are paragraph numbers if you want to reference. We'll go over the book, and we'll talk briefly about I say Lavoisier, I know other people say Lavoisier, so sorry if my pronunciations are bad. Mostly I just read these. And then if we get to part 3, this will just be a couple minutes. We don't get into his pedagogy, which I thought was pronounced it's pedagogue. Sorry, I can't pronounce it right. But I highly recommend checking out those paragraphs as well. They're brilliant. But we'll go into the white parts. This is the book. The one on the left is the original French, you can get from the Smithsonian. The one in the middle is the first English translation by Robert Kerr, doctor and Scottish surgeon, and my version is the one on the left, which is a direct translation of Robert Kerr's. So it could be available for free online for everyone to read. But this was just to get you ready because we're going to get right into it. So let's begin. When I began the following work, my only object was to extend and explain more fully the memoir which I read at the public meeting of the Academy of Sciences in the month of April 1787, the necessity of reforming and completing the nomenclature of chemistry. While engaged in this employment, I perceived better than I had ever done before the justice of the following maxims of Abbé de Condillac in his System of Logic and some of his other works. We think only through the medium of words. Languages are true analytical methods. Algebra, which is adopted to its purpose for every species of expression, is the most simple, most exact, and best manner possible, and is at the same time a language and an analytical method. The art of reasoning is nothing more than a language well arranged. Thus, while I thought myself employed only in forming a nomenclature, and while proposing to myself nothing more than to improve the chemical language, my work transformed itself by degrees, without my being able to prevent it, into a treatise upon the elements of chemistry. The impossibility of separating the nomenclature of a science from the science itself is owing to this, that every branch of physical science must consist of 3 things: the series of facts which are the objects of the science, the ideas which represent these facts, and the words by which these ideas are expressed. Like 3 impressions of the same seal, the word ought to produce the idea, and the idea be a picture of the fact. And, as ideas are preserved and communicated by means of words, and it necessarily follows that we cannot improve the language of any science without the same time improving the science itself. Neither can we, on the other hand, improve a science without improving the language or nomenclature which belongs to it. However certain the facts of any science may be, and however just the ideas we may have formed of these facts, we can only communicate false impressions to others, while we want words by which these may be properly expressed. And that's a summary of what I like to call the Lavoisier's seal on his philosophy between language and science. He goes into that a lot more, but I want to break down this philosophy a lot. So just a quick review. His only object was reforming the language of chemistry. He references Condillac. We only think through analytical methods, so reasoning is just good language. And so while he tried to improve the language, he ended up writing the treatise on elements of chemistry. I didn't really know what treatise was or how to pronounce it, so I kept this slide in case anyone else wanted to reference. It was just a foreign word to me. but I really wanted to explore this. So every branch of physical science must consist of three things. So first, a series of facts, which are the objects of the science. Here I have these interesting formations on rock. The ideas which we represent these facts, so maybe some water came in contact, maybe some air, and then the words by which these ideas are expressed. So this is where we start to get our data collection, our analysis, we start communicating with each other, and we come up with the words that describe what we see. Like 3 impressions of the same seal. So my impressions, and I thought this was kind of funny because I did have 3 different impressions and it just kind of matches. My first impression was the seal just gets stamped over the same thing again and again, like just 3 impressions of the same, literally of the same seal. Then I thought, well, maybe, I don't know much about like wax sealing, so maybe it's 3 impressions that look the same. And then while I was actually making this presentation, I got my 3rd impression, which is why I call these my impressions. And that was that the word was actually the wax itself, a translation of the metal stamp. The metal stamp is the idea. It's it's inverted of the original. It's not the actual casting itself, and it's inverted into the wax. It's not a picture that is put into the wax. It's the negative photo. And the fact would be the original cast that is impressed on the stamp. So the image from the cast is what we want to get onto the wax itself. So of these, I think that the 2nd or the 3rd are the most likely, but I don't know because I don't deal with stamp or with wax seals. And so as ideas are expressed, preserved, and communicated by means of words, we cannot improve the language of any science without improving the science itself. It suggests there's a very intimate relationship between the words we choose and the science we use. And because on the other hand, this is still continues. We can improve a science without also improving the language. I think this gives us an opportunity, if we're ever stuck in a science or we're not seeing any development, that we can start to communicate more. And this communication might reveal to us better ways to improve the science, at least from this assumption, it seems to be, because no one likes it when conversations just seem to be one way and people just talk at you instead of talking with you about things. This one is my favorite. However certain the facts of any science may be, and however just the ideas we may have formed of these facts, we can only communicate false impressions to others. I guess let's just use the clicker to help the sound. While we want words by which this may be properly expressed, this reminds me of Plato's cave. Immediately was the first impression, and also I remember the veil as Plato's naked woman behind the veil, not as the social construct of the veil. So that's the idea that you can't really touch the form. Sort of started to remind me of Descartes. And of course, you start getting into the Matrix, which is from the brain in the vat, which is from Descartes' demon, and it's just all these philosophies combined. But actually, I don't think he goes into this kind of anti-realism. I think he definitely says, as he says, the first thing of every physical science, it must consist of the facts. And so, whether or not we have the facts, the world is the same. There is an objective reality, is essentially Lavoisier's philosophy. How we describe that reality is layered, like an onion. It's we can't maybe really get to the center of it. So when we come back to this expression, it's really just a game of telephone. And for me personally, this hit because it was really freeing. I sometimes have a hard time like expressing myself or finding the right words. This says that even science can't find the right words. So don't feel bad if you can't find your language to express yourself, because we can't do that with objective facts anyways. And I just thought that was incredible. I broke down once reading it to a friend who was in a dark place. But that's the first part. I am way ahead of schedule, so that's good. Usually I talk way too much, and I was worried about that front, so we can actually coast and keep going through this. So we're going to talk more on, we're going to do some more direct quotes because I think it's best to let him speak for himself, and then we'll get into more and more. So, from paragraph 13, it will no doubt be a matter of surprise that in a treatise upon the elements of chemistry, there should be no chapter on the constituent and elementary parts of matter. But I shall take on occasion in this place to remark that the fondness for reducing all bodies in nature to 3 or 4 elements proceeds from a prejudice which has descended to us from the Greek philosophers. The notion of 4 elements by which the variety of their proportions compose all known substances in nature is a mere hypothesis, assumed long before the first principles of experimental philosophy or art chemistry had any existence. In those days, without possessing facts, they framed systems, while we who have collected the facts seem determined to reject them when they do not agree with our prejudices. The authority of these fathers of human philosophy still carry great weight, and there is reason to fear that it will even bear hard upon generations yet to come. It is very remarkable that, notwithstanding the number of philosophical chemists who have supported the doctrine of the four elements, there is not one who has not been led to by the evidence of facts to admit a greater number of elements into their theory. The first chemist that wrote after the revival of letters considers sulfur and salt as elementary substances entering into the composition of a great number of substances. Hence, instead of 4, they admitted the existence of 6 elements. Becher assumes the existence of 3 kinds of earths, from the combination of which, in different proportions, he supposed all varieties of metallic substances to be produced. Stahl gave us a new modification to this system, and succeeding chemists have taken the liberty to make or to imagine changes and additions of a similar nature. All of these chemists were carried along by the influence of the geniuses of the age in which they lived, and contented itself with assertions without proofs, or at least often admitted as proof the slightest degree of probability, unsupported by that strictly rigorous analysis required by modern philosophy, which is, hilarious, I think. It's even applicable to our time. The last paragraph, I'm sorry. All that can be said upon the number and nature of elements is, in my opinion, confined to discussions entirely of a metaphysical nature. The subject only furnishes us with indefinite problems which may be solved in 1,000 different ways, not one of which in all probability is consistent with nature. I shall therefore only add upon this subject that if by the term elements we mean to express those simple and indivisible atoms which matter is composed, it is extremely probable we know nothing at all about them. But if we apply the term elements or principles of bodies to express our idea of the last point which analysis is capable of reaching, we must admit as elements all substances which we are capable by any means to reduce bodies by decomposition. Not that we are entitled to affirm that these substances we consider as simple may not be compounded of 2 or even a greater number of principles. But since these principles cannot be separated, or rather since we have hitherto discovered the means of separating them, they act with regard to us as simple substances, and we ought never to suppose them be compounded unless experiment and observation has proved them to be so. And that wouldn't happen for another 108 years, give or take, with J.J. Thomson, who would come up with his plum pudding model, into the Bohr model, and into our quantum models of today. And so this is the preface for Elements of Chemistry, the first book that really brought the world into chemistry, that everything's made of chemicals. And I kind of opaqued the image on the bottom left because that is much more advanced where we get to later on, but this is the foundation of everyone in this room. And I think it's just so fantastic. This book is the foothold for the periodic table, physicists, nutritionists, and chemistry. It's divided into 3 parts. Each part kind of ties into each other. The first part is the foundation theory, the basic experiments, and dividing up each chapters into the elements. So chemistry of the atmosphere, chemistry of the water, chemistry of vegetables and animals were particularly important to me, researching the history of calorimetry in animals and food, or in people, food, exercise. But there's plenty of other things he talked about. We did talk about fermentation a little bit, which is fantastic, chemistry of metal. His second part is the tables of combinations, talking more about the nomenclature. When this combines with this, what do we call it? Here's the old way, here's the new way. And he really just breaks it all down. This is where we'll start to get into more about where nitrogen, oxygen, and hydrogen turned into their, when it's combined, what do we call it? What's that language like? And here I have oxygen as acid. If you don't know, Lavoisier named oxygen because he thought that was the major component of acid. And so all of the things in the book that he describes as acids are combinations with oxygen. And the third he describes, this is the quote of it, just the instruments for chemistry. And I'll show you some of these here. In the abstract, I said we'll get into some of the works. I'm not going to get into too much of the works. It's just going to be more about these examples. The one on the far left, in the middle, with ABC with the ring, was used to cut glass flasks when heated. And the furnace in the top left middle was used, like, instead of a of the water heater from Mary the Jewess. I think I said that right. It was a furnace with a grill, so that way he could control the heat on the bottom, and the grill separated it, allowing for more control of the temperature of his mixtures. This is the analysis for atmosphere and gases, his tools. This is Lavoisier's original gasometer, a tool that might furnish uniform and continued stream of oxygen gas and experiment in fusion. So I'll try to go a little slower. I got plenty of time. This is also still in the museum in France, and we'll talk a little bit about this in a second as well later on. This was for the analysis of fermentation. If I said the other one was for atmosphere and fermentation, that was wrong. That was for atmosphere and gases, and this one is for fermentation. And just because I feel like I went a little bit fast, this is the one for analysis of the atmosphere and of gases. And just so it's beautiful. These are, I believe they're hand drawn. They're supposed to be illustrated on 13 copper plates. I'm not sure the technique for illustrating on 13 copper plates, but these are some of the copies that, and I'll show you where you get them besides, I'll show you where I got them as well, not just where you can get them from me. But again, this is a fermentation, and then of course of different furnaces, different designs and different combinations. Unfortunately, Lavoisier would be killed during the French Revolution. The arrest of all former tax farmers, which I'll explain in a little while, included Lavoisier. Lavoisier drafted their defense. They were charged with defrauding the state, altering tobacco, basically just being a menace to society and costing the people the money. Lavoisier drafted their defense, but the prosecution basically thought that if persecuting these guys, they would be able to recover money from the state, and so they continued with it. In their last plea to the judge is famous for saying, "The Republic needs neither scholars nor chemists. The course of justice cannot be delayed." Lavoisier was convicted and guillotined on the 8th of May, 1794 in Paris at the age of 50, along with 27 co-defendants. The judge, Coffin Hall, would himself be executed less than 3 months later. So a year and a half after his execution, Lavoisier was completely exonerated by the French government. During the White Terror, his belongings were delivered to his widow. A brief note was included that read, "To the widow of Lavoisier, who was falsely convicted." Lavoisier is a legend. There's a legend that while he was going up to the guillotine, he asked his friend to count how many times he would blink because he wanted to know if consciousness retained after beheading, and the estimate was 18, but this is an urban legend. This is all sourced from Wikipedia, but I just want to say it's a great story. I love it, but people are saying it's not canon. I just still wanted to include it. Lavoisier, a significant portion of his fortune and work went toward benefiting the public. He was a humanitarian, and he cared deeply about the people of his country, often concerned himself with improving the livelihood of the population by agriculture, industry, and the sciences. One of his first contributions in 1765 was an essay for improving urban street lighting to the French Academy of Sciences. 3 years later, he would focus on designing an aqueduct to bring water from a southern river into Paris so that citizens could have clean drinking water, but the construction never commenced. So he switched his focus. Being a true chemist, he tried to turn his focus on purifying the water, and this got him interested in public sanitation. He also was interested in air quality, especially after 1772, there was a fire in a hospital, and so he was trying to understand how to reconstruct the hospital so it had better ventilation, so that patients could have an easier time to breathe or that residues could leave. He also worked on the prison systems. They were absolutely inhumane. He went on and gave many suggestions to the government, and the government largely ignored them or completely ignored them. Prison is prison. He was very difficult to secure public funding for the sciences of the time, an additional, not very financially profitable for the average scientist. I think that's something many scientists today can still relate to. So it was Lavoisier who used his wealth to open a very expensive and sophisticated laboratory in France. So that way aspiring scientists could study without the barriers of securing funding for their research. He also held competitions. Once a part of the French Academy of Sciences in 1768, Lavoisier held his own competitions to push the direction of research towards bettering the public in his own works. He pushed for public education. He founded 2 organizations which are credited were created to serve as public educational tools, a museum and a public school. The Muséum des Arts de Méritis is where his laboratory is housed today, the Museum of Arts and Crafts. And the Lycée, which is the public school, is essentially now considered the pre-college studies for French students. So before you get your bachelor's, I don't know if you get your Lycée or you go to the Lycée, but it's involved in that section. Lavoisier had a vision of public education, having roots in scientific sociability and philanthropy. But this is where he got his money, was investing in stocks. At the age of 26, Lavoisier gained a vast majority of his income by buying stock through the privatized business of government tax collection. Government outsourced their tax collection. Taxes are guaranteed, just like debt. And so he invested in that, and as they became more brutal to get more profits, he got more money. And so while he was still contributing to the public sector, he was still targeted for taking that money and benefiting off that money, which is why he was executed. And so he contributed much more than across many different fields. He also studied to improve tobacco, which is part of his defense. He's like, he created the standards to make sure tobacco couldn't be counterfeited when it was brought into Paris, and the quality of it. He also looked into agriculture, ironically, and he saw that they were trying to understand when these fields had blight, how can we repurpose them? And Lavoisier's report, the _1 prevention of farmers making money was too much taxes. And it's ironic he was executed for exactly that. He was also helped improve the quality and quantity of gunpowder in France after it was deprivatized and brought back into the government, which is actually, Lavoisier was formative influence in the formation of the multinational DuPont chemical company because he trained its founder in gunpowder making in France before his execution. He has many other works. Memoirs on Heat is one that I have read. These other ones are things I'm interested in. I will touch a little bit on Memoirs on Heat. It's beautiful. It touches on Lavoisier's physics. It's also co-written by Pierre-Simon de Laplace. And before you think I spelled the Laplace name wrong, I did not. We spell it wrong today. I would say how he and Lavoisier wrote it would be correct. And I think just the capital L makes it easier instead of going lowercase l, Laplace transformation. And so this Memoirs on Heat is mostly credited in my study of calorimetry, where respiration is combustion, perfectly similar to that of carbon. But this was before the calorie was ever defined. It would be defined in the book from this preface, 1789. This is the machine, because calorie wasn't invented yet. This is the world's first calorimeter. And this picture is from the Elements of Chemistry. It's one of those slides. And so the idea behind Lavoisier in physics is that temperature and thermometers are relatively recent at the time. And one thing they noticed on the limitation is that they measure average temperature, and it takes a while for the mercury to rise, or whatever fluid medium you have. There's time to transfer, and so you can't really capture all the heat of an experiment. And so Lavoisier really wanted to get this idea to capture the experimental heat, and he had this idea of ice. Ice melts from one direction from the heat. It doesn't melt uniformly. So when you have heat from the outside, the ice on the inside maintains. It's also the insulator. When he would measure the temperature of the water melting from the ice, it would maintain its same temperature of roughly 0 degrees Celsius or just above. And this implies that the heat is being transferred directly through the water and into the ice. And as the ice melts in layers, we're getting a direct measurement of that heat transfer. And so what we want to do is create a ball of ice, and we want to put the chemistry inside of that. And that way, the air on the outside won't affect the water melt on the inside. And we just got to measure the water melt on the inside, and we have that direct heat transfer. And so that would be his calorimeter. I should have put that picture back here. But we still cite this today, even though this has notable flaws in this language. I won't get into it, but I will justify Lavoisier in this. He did not say that. That is false attribution. The reasons of respiration blood making is sanguification, if I said that even close, and animal heat, which is particular to the calorie, not considered, but he hopes to elucidate that in future subjects. This was his philosophy. I impose upon myself as a law never to advance but from what is known to what is unknown, never to form any conclusion from what is not an immediate consequence necessarily flowing from observation experiment. And so he's exonerated again. I'm starting to run out of time. I took a little bit too much time on that. So to go over what a calorie was for him, it was a measurement of the repulsive force, whatever that may be, in an abstract and mathematical matter, To Lavoisier, there was three fundamental forces. So the attractive force that brought all of matter together, the repulsive force demonstrated by heat, and the atmospheric pressure that allowed things to not just explode from that heat, to go from 0 to 100, to actually maintain transition states. And so this is quoted from the first chapter, paraphrased. And this is interesting. I thought in chemistry in high school, my professor always told me he didn't understand why the water went from 14.5 to 14.5 to 15.5. It could have been any measurement. And I noticed that it was the room temperature of Lavoisier's experiments in 1783 where the calorie was first defined. And we'll get to this. I only have about 5 minutes, which is perfect because this is going to go really fast. I'm only going to get into these last couple paragraphs. I'm not going to go over all of this, but when updating the language, of course, we were reproached for having changed the language which was spoken by our masters, which they distinguished by their authority handed down to us. But after conversations with many people, Mr. de Morveau bids him, spare no improper names. Those who are learned will always be learned. Those who are ignorant will thus learn sooner. But let's get into his conclusion and how science can save itself. I shall conclude this preface by transcribing literally some observations of Abbé de Cognac, which I think describe, which with a good deal of truth, the state of chemistry, a period not far distant from our own. These observations were made on different subjects, but they will not, on this account, have less force if the application of them be thought just. Instead of applying observation to the things we wish to know, we have chosen rather to imagine them, advancing from one ill-founded supposition to another. We have at last bewildered ourselves amidst a multitude of errors. These errors, becoming prejudice, are of course adopted as principles, and we thus bewilder ourselves more and more. The method, too, by which we conduct our reasoning is absurd. We abuse words which we do not understand and call this the art of reasoning. When matters have been brought to this length, when errors have been thus accumulated, there is but one remedy by which order can be restored to the faculty of thinking. That this is to forget all that we have learned and trace back our ideas to their source, to follow their train in which they arise, and, as my Lord Bacon says, to frame the human understanding anew. But after all, science has made progress because philosophers have applied themselves with more attention to observe, and have communicated to their language that precision and accuracy which they have employed in their observations. In correcting their language, they reason better. That's my presentation. I got one more slide after this, but if you want copies, these are the sources where you can get them. For sure, physical copies of the book are on Amazon. I don't make a lot off it. I'm not trying to advertise it. If you want it for free digitally, you can. I just wanted something I can hold, and Amazon lets you print, basically, if you upload it correct. And that is my speech. I want to leave with this quote. And I will take any questions for whatever time I have. Thank you.
A lot of stuff.
Not really a question, just a comment about the language part of it. Now we expect students to understand quantum mechanics and relativity within the first 1 or 2 years of college, and those are all revolutionary ideas. And human beings haven't gotten smarter over the last several times, like intelligence-wise, we're all about the same. And it just leads to some difficulties in teaching these things. So when you talk about language, it's a language that people don't understand. We're still speaking English, but people don't understand the terminology that comes with science. And now that terminology is getting broader and broader. We still have to teach the fundamentals, and now we're piling all this new science on top of it that people are just to be modern.
Yeah, if I were to comment on that, part of my research is what I've discovered, even from a report from Journal of Chemed, Robertson Schaefer 2014, chemistry students don't understand actually what combustion is. They think all combustion requires oxygen or that it requires a hydrocarbon. And even if you go Google online, Florida State Jacksonville says all combustions are hydrocarbon combustions, which is strictly not true. And so we can't even get the language done with stuff that was invented with Lavoisier too. So I can't imagine how hard it is with quantum mechanics. And I wonder if a lot of our confusion is because of our language barrier. One of the other things I've noticed is that we try to attribute cellular combustion to this form of oxidation, but that's more of the oxidation we've only discovered from the 1920s, not the same oxidation Lavoisier describes as a combination of oxygen, or the same oxygenation as water or our nutritional calories comes from, which is that oxygenation of oxygen, because that's from 1900, and we didn't know chemistry was driven by electrons at that point.
But even Lavoisier commented at one point that human combustion is like burning a candle.
Right,
That are carbon
1783.
dioxide and oxygen, and that's
Right.
centuries old, but still understood that.
Right, but that's actually part of my research. That's a completely false analogy and not actually thermodynamics or physics. And if you want to get into that, I would love to. But I wanted to kind of make this about that. But yeah, you don't actually burn calories. There's no cellular combustion. You're more like a cellular battery than you are a cellular furnace.
You take CO2 in water.
You don't, but your body doesn't transform oxygen into CO2. It transforms it into water, and it transforms the food and water you eat into the CO2. So it's not that direct oxygen to CO2 relationship, and it's not a chain reaction mechanism, which is required for combustion. It's more of an encounterment between molecules. Just using the hydrogen from the reduced NAD and FAD isn't the same as combining with combustion under high temperatures. And plus, every measurable temperature of combustion is well above human sustainability for denaturing. So yeah, I guess we got in my research a little bit, but.
All right. One thing I'll just mention, since language was mentioned several times, those of you who will be going to the national ACS meeting in Atlanta, there will be a whole symposium on chemical nomenclature. So contributions of Lavoisier and his three friends that wrote together this nomenclature, Dr Bourbeau and Croix and Berthollet, as well as Bergman. I saw his name, Robert Bergman was mentioned there. All these will be covered. So if you're interested in nomenclature, please stop by the history symposium on nomenclature in Atlanta. So thank you very much.
Thank you guys.